In this video, we're going to give an introduction to graphing 3D curves and surfaces. So I want to do an example. So let's graph the following in three-dimensional space. In part A, I have y equals x squared with z equals 0. So I have to graph something that satisfies both of these equations. Okay, so in part B is actually something really similar, y equals x squared with z equals 2. So I'm actually going to graph both of these on the same xyz axes. So z, I'll have the x coming out of the board, and then y extending off to the right. And I'll also draw the negative direction, so negative z, negative x into the board, and then negative y extending to the left this way. So for the first graph in part A, the fact that z needs to be 0 for all the points on this means that this lies on the xy plane. And it's since z equals 0. So what this is it's the graph of y equals x squared that lies on the xy plane. So with the additional condition that the z coordinate needs to be 0. So what does that look like? So I know that y equals x squared. We just have to kind of rotate what we typically know that it looks like. So y equals x squared, we know is a parabola. It goes through the origin. That's where the vertex is. But now the y-axis is going to the right. The x-axis is sort of going out of the board. Okay, so that parabola would look something like this curving this way, and something like this curving this way. I'm trying to do my best to make it look 3D. That's why it might look like one side of the parabola is a lot further. This one looks like it's a lot further from the y-axis than this other side is. And that's just because I'm trying to make it look more 3D. It would look a little bit stretched out like this. Okay, so this is graph A. I'm going to label that. So the difference with graph B is that B also has that same curve, y equals x squared, but all the points now have z being equal to 2, which means it's parallel to the xy plane, but the fact that z is 2 for every single point on this curve means it's 2 above it, or 2 higher than it. So if I were to take the vertex, for example, and move that up 2, it would be somewhere here. And now I'm going to sketch that same parabola, but just with everything raised up 2. So this part would look something like this. And another part would sort of extend like that. And that's the graph, whoops, didn't mean to shift that over. So that's the graph to part B. So all of these corresponding points in graph B are 2 higher than they are in part A. So even if I were to take a point here and look at its corresponding point directly below it, that should be 2 higher. Or even on this side of the parabola, look at a point here and the point directly below it, that should be a distance of 2. Okay, now what if I just had y equals x squared, but no restriction on what z needs to be? What would that look like? So if there's no restriction on z, that means that z is free. So let me draw my axes. So I'll have my z-axis, my x-axis coming out of the board, and then y-axis going to the right. I'll also draw the negative direction, so negative z, negative x, and negative y. So what it means that when z is free here is not only do I get to draw this blue curve where we have y equals x squared with z being equal to 0, and also the green curve where z is equal to 2, but everything in between them and everything above the green one and everything below the blue one. So imagine that we take that parabola and then we sort of stack a bunch of parabolas on top of it and a bunch of them below it. What would we get? I'm going to start to draw the one that's on top. So the one that was here, just for reference. Okay, well, let's keep this in green. So the parabola sort of going this way, and this part extends this way. And now what I'm going to do is I'm going to draw a sheet sort of extending down. Okay, so okay, here's how I'll draw this. I'll draw another vertex lower, so over here, and I'll draw a parabola there that has the same shape. So it has one part going this way, one part going this way. And when I connect when I connect this with that point directly below it, this with that point directly below it, and even this point with the point directly below that, I kind of get this parabolic sheet. In fact, I could draw the one in the middle. The one in the middle would look something like that. And it would extend, it would kind of go like that and extend this way. That's the one in the middle. So what we have is our graph is this curved sheet, this curved parabolic sheet shape. And the technical name for this is, it's called a cylinder. So you might be thinking, wait, aren't cylinders those like circular closed things, like the can-shaped things from geometry? So in multivariable calculus, cylinder has a different definition than what we're used to from geometry. So I'm just going to sum that up. So my note is, in geometry, the word cylinder technically refers to what's called a circular cylinder. So a circular cylinder has a circle at the top, then it sort of extends downwards like this, and then there's this circle at the bottom. And that's the cylinder that we know from geometry. But in multivariable calculus, in our class, the term cylinder no longer has to be circular. So we could sort of like unravel this sheet, and moreover, a cylinder in multivariable calculus extends infinitely. All right, so that was just a brief introduction to graphing curves and surfaces in 3D space. We'll see these in much more detail in a later section of this chapter. But the next video, we'll talk about how do we graph regions in 3-dimensional space.